So I'm going to get back to defining what the human eye is. So remember, I'm going to draw a sagittal view of the eye as well as I can, but you have better drawings online in the slides. So the human eye looks something like this. This is the lens that we have here in front of the eye, right? So this is the lens, or rather than the lens, excuse me, the cornea, my bad. And we have the lens behind the cornea right here, which can be moved by these strong muscles that you have that can bend the lens. So this is my lens. And back here in the back of the eye, we have our retina. And the retina is where we have all the sensors. Now remember that there is a blind spot that we have to find, right? Remember that experiment that we did here in class that does not allow you to see specific regions of the world. So I'm sorry if you are all disappointed that your brain has been lying to you all your life, telling you that you see everything, but in fact there's a big black empty space area in your vision for which you have no idea what information there is, and your brain is just guessing all the time what that information may be based on the surrounding information and the temporal information. Obviously our eyes are constantly moving, right? So they're scanning the whole space and then they're just guessing what that information in that missing blind spot is. So that's a very first interesting thing that we talked about with regard to the human eye. Another thing that is really cool is when we look at the retina. So remember, we have an object here, right? 3D object. We have a light source. The light hits the object and it scatters. The light scatters in every possible direction. But for some of these directions, right, the light gets in and gets projected on the back of the brain. And when doing that, then that gets read out by the retina, and that information then is sent to the back of your brain, to the occipital lobe right here, occipital cortex, excuse me, that interprets this, that processes this vision, this visual imaging. Now this retina part, it's a thick layer of neurons that looks something like this. And again, look at the drawings online. You can connect right now into Carmen if you don't have the PDF available, but please go online and look at this because it's going to be very helpful if you do so rather than trying to interpret my drawing. I did not become an artist, I became an engineer. So there's a reason for that. All right, so this is what's going on, and it's really, really bizarre. This is one of the weirdest things you're ever going to see. So the light comes in this direction. Okay, so the light comes in this direction. So this cross section that I'm trying to draw here, this top part, right, is at the very top here, and this back part at the very back of the eye is this thing here. Okay, the very back. Okay, this is called the pigment epithelium. Don't write these names. It's not important. But This is the pigment. I see people writing this, and it's not relevant. It's in the slides, but it's not relevant. This is called the pigment epithelium. And what this is a number of cells that have a certain number of enzymes. They have pigmentation, basically. They have, it's called pigment epithelium because of the pigmentation that it has. And that's similar to the pigmentation that you have in your skin, in your hair, in every other part of the body. Okay? And what happens is when the light, this pigmentation is sensitive to light, right? So when the light comes in, it actually activates the pigmentation and the image gets imprinted in the epithelium, right? It actually is like taking a picture, with photosensitive pigmentation. And once this picture is imprinted here, then on top of this epithelium, and this is what's beyond bizarre, then there are neurons. So first there are rods and cones, so we're going to define in a second. So cones look something like this, rods look something like this. And then there are neurons, other cells, that process that information. Okay? And then finally, when this information has been processed in some way or another, the final ganglion cells send their axons in that direction all the way. So this, at the very top, you have all the axons that come from here that keep growing in thickness because more and more axons are added, and then they get sent all to the back of the brain into the occipital cortex. Okay? You see how this works? But this is what's super bizarre about this. Do you notice what's going on? The light comes in this direction, and it has to pass through all these cells and all these axons before it gets imprinted in the epithelium. That just makes no sense. That's actually terrible because obviously the light is going to come in and it's going to be refracted, right? It's going to start bouncing back and forth between the cells, obviously. What is it going to do? Cells are not transparent. And so it comes in here, it gets imprinted here. This is terrible, right? When you think about this, you see that marker right there? That's what I'm going to do. I'm going to do something spectacular. I'm going to pick it up. All right, to do that, I need to know where the object is in 3D, right? But what's happening is that the light is coming in from here telling me it's here, but I actually see it here. How do I solve that problem? Right? How do I know how the light has bounced about in this cells? And the solution is there is an area in the human eye called the fovea. This is where your macula is. Macula, inside the macula, there's a small area called the fovea, and you've probably seen this if they've shown you pictures of the back of your eye, where that looks something like this, where this, and you have a really good drawing. So this is the epithelium here, right? This pigment epithelium is right here. And then for the fovea, all the cells have been squished to one side, okay? So it looks like this. Now they're all cram up, obviously, on one side. So there are more cells here because there's less space. But in that region, the light can travel straight directly into the epithelium, and this is called the fovea. And this allows you to have great vision, right, at the very center of your eye, which allows you to grab things precisely at the points where you have to grab them and manipulate objects. It's fascinating. So your peripheral vision outside the fovea, the center of your eye, is terrible. But the center of your vision at the fovea is extraordinarily high. And most of the rods and cones are in the fovea because that's where you want more resolution. And as you go away from the fovea, you have less and less resolution. So this, your human vision could be could not be more different than a camera. A camera has the same number of pixels at the periphery as at its center, right? The pixels are uniformly distributed across the image. The human eye is nothing like this. At the very center of your vision, you have huge number of pixels, and as you go away from that center, you have less and less and less, and it's almost it's a Gaussian distribution, right? It's almost Gaussianly distributed. Right? When you get to the periphery, you basically have no vision. Okay. All right. Now, as I said, you have two types of cells that read directly. So the first neurons, or cells that read from the epithelium, is another thing I could say about the epithelium, by the way, because it's pigmentation. Depending on which pigmentation you have in your skin, that also has an effect on the pigmentation on the eye, obviously. So people that are what's the word for this? Very pale. It's albanium. That's correct. If you're an albino, you lack pigmentation in the skin. You also lack pigmentation in the epithelium, which actually makes your vision really blurry. Okay, so it's actually a serious problem, not only because of the skin problems, but because of the vision problems, right? There's this relationship here, obviously, because it's pigmentation. So then, on top of that pigmentation, or that epithelium, you have the rods and the cones. The rods, which are the most numerous in the retina, they read black and white information. They can only read grayscale, right? Black and white. That's most of the human vision. And the cones can read different wavelengths, which we call colors. Now, two things about this are going to blow out your mind. Number one, color does not exist. Sorry to tell you, I know it's a disappointment. Things are beautiful in color, but color it's an illusion. Like the blind spot, color it's an illusion, right? So what happens is that light, other than a particle, the photon, it's a wave, right? And that wave has a frequency, right? And that frequency in the visual spectrum is the frequencies that we can see, that the human eye is tuned to. The human eye has decided to divide this into three main frequencies. We call the low, mid, and high frequencies, right? And it has decided to, or we humans have decided to call the first type of frequency, right, blue, and the other one red, and the other one green, right? Because they approximately correspond to these so-called colors. But these are just frequencies of the same light, right? So the light doesn't have color. The world doesn't have color. Your brain says it has color, but it's just assigning a category of color to a specific frequency to that electromagnetic wave, right? So the world is just electromagnetic waves. And your brain says, okay, I'm going to call this frequency from this band to that, from this value to that value green, and from that value to the value blue, and from that value to the value red, and so on, right? Okay, fine. But and if we could see in infrared, we could say, okay, this is infrared, and so on. But colors don't exist in the real world. It's just ridiculous. It's just frequencies. So that's the first fact. So your brain has been lying to you because you have a blind spot that you didn't know about. It's been lying to you constantly because it's telling you that there is color in the world when there isn't. But okay, it's just a way of saying this frequency band is red, and this frequency band is blue, and this other one's green. Fine. What happens is that most of your retina, right, where all the sensors are, all of this, most of your retina does not have color sensors, doesn't have cones. It only has rods. So basically, you just see in black and white. And you see color mostly in the fovea, right? In the fovea is where you have most of the color sensors. So all the periphery, all the peripheral vision that you see, I know that you think you're seeing vision in the periphery, right? But you don't. Believe me, trust me, you just don't. it's black and white, but your brain is lying to you again, saying, well, I can make a good guess of what the color of that object is, either because you've moved your eyes before and you know, or because it's just making a guess, right? So the brain's again lying to you, just trying to make a guess of what the color is. So the best way to test this is today at home, you ask a friend, as you look straight ahead, don't cheat obviously, just look straight ahead and ask a friend to select a colorful object and bring it very closely until you can see it, and you'll see that you can tell what the object is way before you can tell it what color it is. You just not, because with the periphery you can see the object in black and white, you can recognize the object, you just can't tell its color. Okay, easy to do at home. So anyways, we actually mostly just see in black and white. We have, I think it's about 100 million rods. Yeah, about 100 million rods, which allows us to see in black and white, and only 4 million cones. So 4 million over 100 million. That's a good ratio of luminance versus color. Now, as I said before, black and white, we're not going to say black and white, we're going to call this luminance, right? That's the amount of illumination or light that I get. It's a value of intensity, and that's called luminance, okay? And if you take computer vision, we're going to talk more about this, but basically, imagine that you have an image which is in RGB, okay? So each pixel, the pixel I in my image, has what's called 3 channels. Each channel defines the values of intensity for each of the 3 basic colors that we usually use to define a color image, right? Now, you're going to think that color is 3-dimensional, right? I mean, it makes sense because of R, G, and B, right? But it's not true. Color is not 3-dimensional because that vector of 3 elements is 3 channels, include the information of luminance and color. Now, color technically is called isoluminant color. Isoluminant means without luminance. So when I subtract the luminance from my image, all I have left is color. And luminance is nothing else than a linear combination. It's a function of R, G, and B. Usually it's just, let's call it alpha R plus beta G plus gamma B, right? Just a linear combination of R, G, and B, and that is luminance, right? So when you convert an RGB image to grayscale with MATLAB, for example, what it does, it takes a linear combination of R, G, and B, right? I mean, the simplest one is you assign ones here. So you have R plus G plus B, maybe divided by 3, if you will, right? And you get your grayscale image. That is luminance. And luminance allows you to see objects in 3D, right? Because it defines what is called shading, and we'll spend quite a bit of time later in the course talking about shading and how to recover shape, 3-dimensional shape, from that shading information. Okay, which is called shape from shading. That's what luminance allows you to do. Color is what remains in that vector once I eliminate that dimension. Okay, so what's that dimension? Let's think about this. So I'm in 3-dimensional space, R3, which is given by the basis vector, like call it first basis vector R, second G, third B, right? That define the 3 RGB channels of my image, right? Now, when I compute my luminance, right? Let me call this luminance L, my vector L. My vector L is going to be defined here in some direction, right? It's a vector in 3-dimensional space, right? Now, if I change that luminance, right? All I'm doing is I'm moving around this 3-dimensional space, right? Now, if that linear combination defines the true norm. Let's simplify this. Let's say that this linear combination defines the true norm of a vector, okay? To simplify this, then this vector can move about the two-dimensional sphere, right? S2, the sphere, right? And what is color? Color is what remains when we eliminate that luminance, that's the sphere, right? And the luminance is the vector that I have eliminated, right? So color is defined by S2 and luminance by the norm of my vector, right? In that case, the true norm, because I'm assuming I'm using the true norm, right? You see? So color is two-dimensional. It's not three-dimensional, it's two-dimensional. And in the human retina, there is a process that occurs somewhere around here which computes these two dimensions, and they are called opponent colors. And you can, don't write it down, you can write the name down, but don't write too many details. You can Google this later and see opponent colors, and you'll see what they represent, how they're computed. It's actually pretty cool. That's how the human retina does it. For computers, you can compute color spaces in a variety of ways. There are many algorithms to compute different types of color spaces. The opponent color is very popular, obviously, because that's what the human brain does. But it's not the unique one. But all the color spaces have to be two-dimensional, okay? Which means that these three different types of cones, we have three different types of cones in the retina, right? Have to be combined in a way to produce these two dimensions, right? Because these three different types of cones have information of the luminance and the color, and they have to factor this information out, and all this is done here by the neurons, the cells in the retina. Now, when your doctor or your optometrist looks inside your eye, right, with special equipment, they're actually seeing the neurons in the retina. And these neurons are part of your brain. So in fact, your optometrist can actually look into your brain by just looking inside your eye, because this is part of the processing that occurs in the brain. Okay? All right, there are many other types of processings that occur in the retina that are related to shading, that maybe if we have time we'll talk about it. Also about motion and some other important things that we may, if time permits, talk about. What else? Focal length. The focal length of the human eye is generally computed. The distance between, you see the cornea here, where the cornea is and where the lens is. So right here at the midpoint between the cornea and the lens and the back of the eye, that's called the focal length of the human eye. And for the human eye, of course it varies in the population, but it's pretty constant in all of us. And it's approximately 0.017 meters. And remember that when you want to focus at things that are different distances, right? Or you want to zoom in or zoom out, or things that zoom in, zoom out like a camera, but with your vision that's just focusing in things that are farther away or closer to you, right? The human eye cannot move the lens, so it cannot change the focal length. So the way it does this is it bends that lens with the muscles that have drawn there. And by doing that, it changes something is called the optical power, okay? That is equivalent to what we have seen for camera lenses. Now, the optical power is measured with optical power is measured with something that you may be familiar with. Anyone wants to make a guess? How I, distance, I measure it usually meters or inches or yards, what have you, right? What do you think I'm going to measure the optical power with? Diopters, that's right. So this is given by diopters. Now the optical power is defined as the inverse of the focal length, so 1 over f, and that is what we call diopters. So the average, so to speak, optical power of the human eye is 1 over 0.017. So the optical power, is approximately 1 over 0.017, which is approximately or equal to 58.8 or approximately 60 diopters. Now I know that you're wondering like, oh my gosh, do I have 60 diopters? Yes, you do. When you go to the optometrist and they say you have 1 diopter, they mean you deviate from that 60. Okay, that's how much you deviate from that 60. Now, how can you use that, or rather, how can you use the equations that we've derived for lenses to determine what you can and cannot see, right? And this is actually the equation that your optometrist uses. Maybe she or he doesn't know, but it's implemented in the devices that they use to compute the number of diopters that you need for your glasses, right? How do they do that? Well, they use an equation that we have already derived, which is called the lens maker's equation. Remember that? So you can use the lens maker's equation, which remember is 1 over z prime plus 1 over z equals 1 over f. This is obviously the optical power that we just defined. And now if you plot this, you're going to see that you get, so here this represents z, right? And I'm going to represent z prime here, right? Remember, outside the camera, inside the camera, in that case, outside the eye, inside the eye, right? Same thing. So you're going to see that, let's see, if I have, I'm going to divide this, let's do this. I'm going to divide this by 0.1, maybe it's 0.3 here, maybe, actually, why don't I use the log? Let me use log coordinates because otherwise it's going to take forever. So I'm going to do 0.3 here, 1, 3, and maybe 10 meters. Okay? So this is the distance from the cornea, or from rather the point between the cornea and the fovea and my object in the depth direction, right? In the k direction. So this is z, and this is z prime. And what happens is that you're going to get something like this, a function that looks like this, okay? If you plot it using this equation with that parameter that we've derived, 60 diopters, and you will see that everything basically fits in about, what is it? About 17 millimeters, right? Which is the focal length. Okay, great. And note here that about 1 meter, that means anything that's at least a meter away from me, it's focused without me needing to change the lens, right? Without moving the lens. Everything that is at 1 meter or more, it's automatically focused, right? Or almost. But anything that gets closer requires me to change the lens or to adapt the lens so that I can focus that object, right? And as you get older, and I don't know if there's an old person in that room, maybe me, right? When you get older, the closer objects are, the more difficult it is to focus, right? And that's because the lens tends to actually thicken, get really thick, and they get harder and harder to bend, okay? And unfortunately, most of your cells in your body change over time, right? I think, what is it, the liver, you basically wake up with a new liver, right? Completely new cells every 2-3 days or every week, whatever it is, right? And the liver regenerates really fast. It needs to, because it does a really nasty job. The bones also regenerate, but take years to change all the cells, years, right? The cells in the lens of your eye never change, right? They're stuck. So when you get older, they're old cells, they hardened, that's it, there's end of story. Then you need glasses to read up close, right? To read a book, to read things that are about 1 meter or less in distance, and that's why. All right, now this is the human eye. After the human eye processes that information, and as I said, there are cells here, there are so many cells here, you wouldn't believe, so many neurons. I mean, it's absolutely insane the amount of information that is processed here. So remember, you have about 100 million rods and 4 million cones, right? So your resolution, your camera, so to speak, in the human eye, it's 104 megapixels, right? That's your resolution. But that would mean, if you were to process that information, that you have to send through that blind spot 104 million axons. I don't know how small you think that these cables, these axons are of the cells, but they're not that small. If you have 104 million of them, they're probably something like this. Then you would not have a blind spot here. You would have a blind eye. So what does the human brain do? It compresses the information, and it only sends 10 million pixels to the back of the brain, to the occipital cortex, okay? To an area it's called V1. V1 stands for Vision 1. I mean, scientists are very, very good at inventing names. That's why they are scientists and not English majors, right? They come up with these very fancy names like V1, Vision 1. It just means the first area in the occipital cortex that processes information coming from the eye. Now, vision in general is very complicated. I'm going to cover as much as I can regarding the image processing part of the image here in this class. And then if you're interested in the topic, I suggest next academic year, you take computer vision, which covers more of the high-level vision components of computer vision and image processing. But I ought to say at this point that the problem of vision is very, very complicated. It's extremely difficult. So of the brain, this huge mass of meat that you have in your skull, that consumes about, so the brain, if I'm not mistaken, I'm speaking of out of memory, so I may be wrong, but I think it's about 2 to 3% of the weight of your body, okay? But it consumes about 30% of your calories. That's a pretty good calorie to weight ratio. It's tremendous, right? The amount of computation that this machine does. Do you know what portion of the brain is devoted to vision, to solving the vision problem? Anyone wants to make a guess? Make a guess. What do you think? No one wants to make a guess? There's no wrong answer. It's a guess. What is it? What part of the brain computes is dedicated to computing or solving the problem of vision? No, percentage. What's a percentage? What's part of how much of the brain is used to compute to computations that solve the vision problem? 15%. Okay. What else? What? 10%. Anyone else? 40%. We have 40% there. Okay. Anyone else? Okay. Everyone laughed, but it's actually 50%. So very good. Very close. It's about 50%. There's debate on how much because we don't know everything about the brain yet, obviously. But it's about 50%, maybe a little more, maybe a little less. But it's huge. Vision, it's a very, very difficult problem. It requires most of your brain, basically, to just solve that problem. That's why it's so interesting, too. Before the images get into the occipital cortex, they actually pass through another area in between the eyes and the cortex, which is called the LGN. And in there, it gets processed even further. It gets processed in the retina, it gets processed in the LGN. And there is a certain number of computations that are done. So basically, just to summarize it really, I mean, this is really, really simplistic, but each cell basically has what's called a surrounding field or a field of view. And what that means is that if I'm looking at this whiteboard, there is an area here in the inside and a surrounding area in the outside. And depending on whether this area is active and this is not active, or vice versa, this is not active and this is active, meaning there is light here but not here, or there is no light here but light here, then the cell fires. Okay? So basically, your vision only responds to changes in luminance, not on luminance itself, right? So this is also very easy to test because this is not unique to vision. That's throughout the body. The body works like this for all the senses, right? So if you're wearing socks, without looking, and if not, do it tonight at home, without looking, try to point exactly with your finger where the top of your sock is in your leg. And you'll notice it's really hard. And the reason is because your brain has, or your cells in your leg have stopped responding to that pressure. Now, when you put them on, you know exactly where they are. These cells are firing like crazy. It's like there's something giving me pressure at that particular point with the band, right? The elastic band. But after a while, they just say, well, I've already sent the signal. I'm not going to keep sending the same signal over and over and over again. That's the same that happens in the retina, right? When there's a change in luminance, the cells fire. When that luminance is constant, the cells stop firing, right? So there's a famous experiment that goes way back when we didn't have technology to make these experiments humane. So they came up with this idea that you could wear a contact lens that had a little stick sticking out of the lens, and you'd put an image at the end of the stick so that the images would move with your eyes. So what that means is that the amount of luminance that you got at every point in your retina was constant, right? And what happens when you do this is that you go blind because your cells stop responding, right? Now you can do these experiments with technology and it's a little better, but still there's some debate on that, but to a large degree that still stands. So these are the receptive fields, and the receptive fields, the first layers are very small, and then at the consecutive layers, they are a combination of these small receptive fields, so they're larger receptive fields. And at the higher levels, they are combinations of these larger receptive fields, so they're even larger, and so on, right? So if you have heard of convolutional neural networks, which is some of the neural networks used in deep learning, this is basically what they try to emulate, right? They try to emulate, so you have computations that are done in a receptive field that is very small, meaning a small region in the image. And then once you have done all these computations, convolutions basically, because these cells basically do convolutions, similar to Gabor filters. If you know what that is, and if not, we'll cover this later in this class. And then on top of that, once you have these convolutions, then you do convolutions on top of the convolutions, right? But at a larger receptive field, and then at an even larger receptive field until you have the whole image, right? And that's basically trying to imitate this structure. Now this structure was discovered by Hubble and Wiesel when they were studying the retina and the LGN cells of the cat, which are actually very similar because it's a mammal, very similar to the humans. And they actually won a Nobel Prize for that discovery, right? It is that important. Okay. So that is at the first levels of computations that occur both at the retina and then at the LGN. And then once you get into view 1, there's more processing like this. And then after that, we don't really know what happens. But what we do know is that there are many areas in the visual pathway that are involved in trying to decode objects, 3D structure of these objects, infer properties through color, through motion, through shading, and so on, right? So we know that there are lots of these computations. But the point that I want to make with that is that we are going then from the realm of imaging that I'm talking here, and that's what I'm going to cover in image processing, that the same thing applies to cameras. We're going to do image processing, meaning we're going to process the image, to then the realm of perception, visual perception. And visual perception, this is high level, right? You assume that you already have processed the image somehow, and now you have something you can work with, and you can recognize objects, you can recognize actions, you can recognize colors, you can recognize emotions, and so on, right? All these things are part of perception, not part of image processing, right? Once you get into perception, then things become really complicated. However, I'll show you just a couple of examples of this. I have here some slides. Well, rather than a slide, some online images that I found. All right, so here's the first one. Remember that I told you about Vincent van Gogh. This is one of his paintings. And when you look at this, it looks like almost an ocean rather than a field of, I don't know, cornfield or flowers, whatever this represents, right? It gives this wavy impression. And as I already mentioned, this is because the horizon line, which is here, right? The horizon line, remember, it's defined as the line where all the parallel lines on that plane converge, right? So all the parallel lines have to converge on that horizon line, remember? But this is not what's happening here. The way Vincent van Gogh actually painted was that the horizon line had some areas of interest, and the parallel lines converge within that region of interest. So sometimes they converge here before or south of the horizon line, sometimes north of the horizon line, right? Sometimes more to the left, sometimes more to the right. And that's what gives you this impression of this is not a solid ground, right? Pretty cool. And that's perception. However, this perception is because we're playing with how the image is processed at a very fundamental level, right? So your brain is actually interpreting the line at infinity, meaning the horizontal line, right? Interpreting that line and then making estimations of how the 3D world looks given a two-dimensional image. And it's making mistakes because the information that it's given is wrong, right? And here's another example. This one of my favorite examples. This image looks just so off, don't you think? I mean, this is fantastic painting. When you look at this, there's nothing really wrong with it, but everything seems to be wrong with it, right? The shape of the people, the objects in the picture, they all seem to be somehow misshaped, right? And the reason for this is that this painter, when he decided to create this painting, he decided to paint it from 4 different locations, okay? So first, he placed himself right here in front of the couple who were to be married, right here, and start the painting, part of the painting, okay? Then he moved to the left about this position and continued painting. Then he moved to the top right, somewhere around there, and continue. And then finally moved to the top left and finished the painting. Now, the vanishing points, right, or the center points, when you look at this, there are 4 central points. One is right here at the center. This is the frontal view, obviously. One other one is right here. The other one is here. And the other one is here, I think, or maybe here. So obviously, when you combine 4 different points of view into one and you stick it together, things look weird, look out of order, but somehow the brain has to make sense of it, right? So it's just trying to understand what's happening, and it just sees things deformed, but pretty okay. It's not so bad, right? When you look at this, you go like, I believe the picture. I believe it. I know there's something wrong, but I believe it. I think that that's one of the most fascinating paintings for me, just because it can be explained so well with the things that we are covering in this class. All right. Now, there is a documentary that you may want to watch about this famous Dutch painter. I'm blanking with the name again. The painter that painted this famous women with a white pearl, remember? What's the name? Anyone remembers? Yep. Question? Which shadow are you talking about? Oh. Uh-huh. Right. Right. How does the camera do it? No, the camera only captures it converts the electromagnetic wave into a number, right? And then when you print that in a screen, then your human eye interprets this as that color. It's not that it's a color in the screen, right? The screen doesn't have a color. The screen, as the world, all it is, it generates electromagnetic wave at a specific frequency. And it is your eye that interprets that frequency as red, white, what have you. Make sense? I talk quite a bit about color vision and computer vision. I'm not going to talk about this here because although this could be considered image processing, we just don't have time in this course, but it's a fascinating topic, color. Anyways, what were we talking about? Oh, that painter. Anyone remembers the name? What's that? Vermeer. That's right. Oh gosh, I can't believe I forgot about it. So Vermeer, there is a documentary about Vermeer that claims that Vermeer, I mean, when you look at Vermeer's paintings, they look extraordinary. I mean, he must be one of my favorite painters of all times, right? It's like looking at an actual picture taken with a camera. It's extraordinary, the detail, the lines, the accuracy of the characters that are portrayed in the paintings. Absolutely incredible. And what is surprising in the art world is that when you look at his history, there is very little on his training. Because usually training in any trade, right, especially in the old days, was passed down from specific masters to students, right? And you cannot really find this for Vermeer. It just seemed to pop out from nowhere. Now, could he have been a genius, an absolute genius that didn't need any training? Of course. We've seen that before. But it's unlikely. So either that information has been lost, which is possible, or there is something going on. And what this documentary suggests is that that something is the discovery of the camera obscura. Now, at that time in the 1700s, cameras didn't exist as a picture to take pictures. But what did exist was the knowledge of perspective projection. And what they suggest is that lenses already existed, that what they actually did with a lens, they projected the scene that they have on a canvas, and they only needed to paint the canvas according to the actual figures and colors that they actually saw, right? Now, the person that did this documentary, to prove his point, he actually designs that system and starts painting. And this is a person without any training on artistic training or on paint or anything. And I mean, I have to say, the paintings that he paints are pretty good, right? Well, he paints just one, basically, but it's pretty good. The result is pretty stunning. So is it possible that some of these painters at the time were already using the idea of the pinhole camera, right, to come up with a way to get better paintings? It's plausible, at least, right? We have to entertain the possibility. All right, excellent. So, back to equations. Can someone try to get back the lights on? Thanks. All right. So moving on, we're going to talk about geometry, a lot of geometry in the next few weeks. And then after that, we're going to go to radiometry. That's where we're going to talk about light and shading. And then after that, we're going to talk about other topics in image processing, like compression and so on, communication, sending signals or images in that case. But let us start with geometry, and in particular, I want to start with the geometry of multiple images. This is one of my favorite topics in image processing. And the reason is not because I necessarily like this topic more than others, but because this topic is so formal, so mathematical, that it's so easy to understand. Okay, once you understand the basic equations, you understand everything. It's just it follows from the mathematics. Now, I'm not going to cover the most interesting part, which is projective geometry, but at least we'll cover the essentials. Now, imagine that you have a two-dimensional image, just a one two-dimensional image. Can you recover the three-dimensional information of your world from that two-dimensional image? What do you think? In general. No? I see a no. Anyone else wants to? Yes? I hear a yes. Okay, no one else? No? Okay. No, in general you can't, right? And the reason is that a two-dimensional image has X amount of information. And a three-dimensional image has more than X amount of information, right? And you cannot convert X amount of information into 2X or anything larger than 1X, right? You just can't. Like, if I have 1 kilo of sugar, doesn't matter what I do to the sugar, I'm not going to get 2 kilos of sugar, right? I can eat part of the sugar and get less than 1 kilo, but I'm never going to create sugar out of nothingness. Information is the same thing. I love this because whenever you see these TV shows like CSI and things like that, and they have this picture of a license plate in really low resolution, and they'll say, oh, but I have an amazing image processing algorithm here that's going to show me the exact number of the license plate by enhancing the image. Like, what are you talking about? If you have X amount of information in your image, all you have is X amount of information. There's nothing you can do to the image that's going to create 10X. That's wishful thinking. It just doesn't work. That's the importance of Shannon, right? What Shannon taught us is that information is like anything else in the universe, right? Physicists take this very seriously. I mean, right now, information is one of the most important topics in physics, right? Universe is just information, right? And what happens when information gets in a black hole? And is the universe losing information? That's inconsistent with their theories, and they talk a lot about this, right? And that leads to all these weird theories that they say that the universe is actually two-dimensional and that we have a hologram that's like three-dimensional, right? And so on. This is Susskind's theory at Stanford, things like that. Well, because information cannot be created and cannot be destroyed, so they have to justify things somehow. Information is like anything else. It cannot be created, cannot be destroyed. Okay. So that cannot be done unless we do something, which is we assume, right? We make some assumptions about our world. If we can make some assumptions, then we can recover 3D information from 2D images, right? But we have to make some assumptions. Without assumptions, there's nothing we can do, right? Now, this is not unique to image processing. Anything in science, in engineering, depends on assumptions. Even mathematics depends on assumptions, right? In mathematics, the assumptions are called axioms, right? So for example, there is an axiom in mathematics that says, if I have 2 points in two-dimensional space, they're connected by a line. And I'm not going to prove this result. I'm just going to take it on face value because I believe in it. Right? This is an axiom. It's an assumption. It's a hypothesis, right? Now, you may think that this is really, really good. I mean, obviously, 2 points are connected by a line, but there are many axioms in math. One of them is the axiom of selection. The axiom of selection says that if I have a box with elements, right, with objects, say balls, I can always go into the box and pick one of them, right? It's axiom of selection. mathematically, if I have a set, I can always select one element of that set, right? Well, seems obvious too. Why shouldn't we assume that? But it's not true. That's actually false. And if you take this, if you believe this assumption, if you believe in this axiom, then you can prove, this is called the Banach-Tarski paradox, you can prove that you can take a ball, a three-dimensional ball of radius 1, and partition it in a finite number of pieces, translate these pieces, rotate them, put them back, and end up with 2 balls of the original radius. Oops. So obviously, it's impossible in the real world. I cannot go out and buy an apple or an orange and cut it into a finite number of pieces, translate them, put them back together, end up with 2 oranges. Otherwise, it would be very nice if we could do it, but we can't, right? So obviously, this axiom is wrong. But why do we have this axiom? Because if we don't have that axiom, then there's very little we can do in math. So there are mathematicians that are very pure and believe only in axioms that are believed to be true and refuse to work with this axiom. But then there's very little they can do because, you know, when you do a proof in math, you have to use things that you already know are true, right? I mean, that's a proof. A proof is to reduce your current problem into one that has already been solved. So that's why people use that axiom, because it allows them to get the results that they want. That's exactly what we're going to do here, right? We are going to work with problems that we know, or assumptions rather, that we know are not always true, but that they're generally true and are going to allow us to extract 3D information from 2D images. Okay, there's one more thing that we can do. The human vision does not only work with one camera or one eye. It uses 2 cameras, 2 eyes, right? Why would that be? Why do we have 2 eyes? I mean, it's a little weird, isn't it? Why 2? Why not 3? Why not 5? We'll get to that, actually. So the reason you have 2 is because of something called triangulation. Okay? So imagine that I have 2 cameras. If I observe this particular object from one camera, I have an idea what this object looks in 3D, but I'm not sure. But if I have another camera here, I get another idea of what this object is like. And combining this information, I can reconstruct it, right? And it's called triangulation because this point right here gives me a point in that image plane, gives me another point in that image plane, and that defines a triangle. You see this? And that triangle is going to allow us to reconstruct this object in 3D. Okay. Now, if I have 3 cameras, not 2, but 3 cameras, can I reconstruct that point, this 3D-dimensional point, more precisely? And the answer is yes. The reconstruction is better with 3 cameras. However, the amount of computations that you need to perform to get this minimal gain are tremendous. So the evolution has decided, 2 cameras is sufficient. You get close enough to the 3-dimensional reconstruction for what you need to do. The amount of brain tissue that you need to compute information of 3 cameras is just too much. You wouldn't be able to hold it in your body, right? So it's decided 2 is optimal for what you need to do. So there you have it. You have 2 eyes. Now I'll talk about this also. You do not need 2 eyes to get 3-dimensional information. In fact, and again, you need a friend for this, but if you get a ball or maybe a bottle, if you have a bottle with a bottleneck, right, it's pretty thin, that's the best way to do this. And you ask, so you close both eyes and you ask a friend to put it somewhere in front of you, right? And then with one eye still closed. You open the other one, and you try to reach inside the bottleneck, right? And you'll see that you get pretty close, but you fail to get exactly at that position, right? But you get pretty close. And the question is, what's going on here? How can I get this close without triangulation? And the answer is depth of focus. So when your eye has to focus at a particular object, it knows that the amount of bending that I need to do in my lens is proportional to the distance from the object to my eye, right? And that gives you a very good estimate of the distance of the object. And with the camera, you can do the same thing, right? You can move the focal length until the object or that point of the object is at focus, and then that gives you a small range of distances at which that object can be, right? So these are ways that we're going to see on how we can recover three-dimensional information. So let's start with two views, two cameras. Now, for two cameras, we're going to talk about what's called epipolar geometry. So let me draw this. I have two cameras, and I'm just going to draw the image plane, and in fact I'm going to draw the normalized image plane in front of the pinhole, okay, to make things easier, because this is right side up, right? The image is right side up instead of upside down, okay? So here's my camera 1. And here's my camera 2. Okay. Better. Okay. Now, I'm going to draw the projection of a point, a three-dimensional point, onto these two image planes. So here I have my three-dimensional capital P point, and this goes through the pinhole. Now remember, I'm drawing the pinhole behind the image plane, right here, okay? That's my pinhole. I'm going to call this O, okay? That's the pinhole of the camera. The real physical retina is behind it. This is the normalized plane in front of it, right? And where that ray, that OP vector, pinces or crosses the normalized plane, let's call it pi, right? Here I have my image point, small p. Yep. Now I'm going to do the same thing here for my other O. I'm going to call it O prime vector. And that's going to give me my small p prime vector. And I'm going to connect these two origins, these two pinholes, with another vector, the O prime vector. Okay? And this is O prime P vector. So far, so good? Any questions? Good. So now let's draw this, or let's write this in an equation form. So I'm going to consider my O prime vector first, okay? This is this vector right here, right? And I'm going to do cross product of this vector with either this or that vector. It doesn't matter. Let me choose O prime P prime vector. This is a small p, so I'm going to choose this vector right here, okay? Okay. I'm choosing P prime instead of capital P because capital P is unknown to me, right? What I do know is O prime P prime. I don't know this other one, but I do know this one. Okay, so I'm going to do cross product of these two vectors. Now, what's the cross product of these two vectors? It's a normal vector, right, orthogonal vector to that plane defined by that triangle, right? So if I multiply now this normal vector by another vector in that plane, this is going to be equal to 0, right? Do I have another vector in that plane that you already know? OP, correct. This O small p vector, right? So if I multiply this by O small p, that has to be equal to 0. Now, here I am assuming the cameras are already calibrated. We'll get to the uncalibrated case in a few minutes. Now, let me try to write this in a nicer form. So, let's see, this vector, O prime, this is the same, remember, as the translation, right? The translation of the coordinate system, the origin of the coordinate system, from the plane, I'm going to call this plane pi prime. So from pi prime to pi. Okay? And for simplicity, I'm just going to call this t. All right? To simplify notation. All right. The OP, this vector here, the O a small p vector, what's this equal to? This is equal to the OP vector right here. Right? This vector, it's the same as this one, right? But rotated. Right? So I'm going to define this rotation as the matrix. So this OP vector, you can also write this OP vector if you want to as P given in the coordinate system pi, right? And now the rotation from pi to pi prime, right? Oops. Right? No? Okay. Now, here remember if I'm going to write my P, small p, as UV1 transpose and P prime, I'm going to do U prime, V prime, 1 transpose. Then I can rewrite this equation as P, right? OP, I'm just calling it P. I could call it P pi, but I'm simplifying notation, right? Just call it P. And then I have this matrix here, which is translation, right? O prime, I call it translation, right? Cross product with this OP prime, right? Or O prime P prime rather, here, which is a rotation of P. So this is the rotation of my P prime, and this has to be equal to 0, right? Okay, so what I'm going to do, I'm going to take this cross product, I'm going to call this E, and I'm going to write P, E, P prime equals 0. And what's this E? E, it's a matrix, which is, E has to define a cross product, but it has to define it using an inner product. And the reason I need to define it as an inner product is because this is a matrix. So I have to convert a cross product into a matrix multiplication. And I can do that using this trick. This is a famous trick. This is called a skew symmetric matrix. For reasons that will become very clear right now. So what I'm going to do, if T is equal to T1, T2, T3, I'm going to write negative T3, T2, T3, 0, negative T1, negative T2, T1, 0. Okay? So here's what I'm doing. Imagine that you have here the vector T and the vector T, zeros in the diagonal, and then this is positive, negative, positive, positive, wait. Oh no, yeah, this is positive, 0, negative, negative, positive, and 0. Okay? So you see that this matrix is symmetric except for the negative sign. And that's why this is called skew symmetric. Okay? Good? Okay, this matrix right here, E, is a famous equation. This matrix right here is so important that people have called it, and name stuck, the essential matrix. And you can't believe how important that matrix is. You'll see. All right, super important result. What do we want to do with this? This is what we want to do. My goal is to recover all the parameters of that equation from pairs of points P and P primes. Okay? So if I know that this P corresponds to this P prime, and I know this for a certain number of points, then can I recover all the parameters of my essential matrix? That's what I want to solve. Do we know of a technique that we may use to do that? Oh, come on. Linear least squares, right? Okay, so we'll get there. So let's say that I have recovered the essential matrix with linear least squares, and I have E. I have recovered E. How can I now recover from this the rotation matrix and the translation, right? That's going to tell me what is the rotation between these two coordinate systems and the translation between them, right? This obviously, I don't know that. I mean, if I knew, that would be much easier, but obviously you don't know these things. Okay. So what I'm going to do, I'm going to compute E transpose. Let's see what this is equal to. I think I'm out of time, am I? All right. We'll do that next week then. Have a good weekend. Work on the homework.